Okay, so last we were talking about buffering. So buffering kind of allows us to sit there and make it so that our pH has some room to sit there and be flexible. Okay, and so often we'll use like weak acids or weak bases to act as buffers so that we can sit there and have a little play with that pH. Okay, our blood is an example of that. What is the pH of your blood approximately? Anyone?
Oh my gosh. I feel like I should know this.
Good. What are you mostly of? What is your body?
Water. So it's 7 something.
Yep.
So like 8. Oh, never mind.
Nope. If it's 8, it's a problem. There's seriously something wrong. So your pH is around 7, right? Because you're primarily water. And so your blood has actually various components in your body to sit there and help you buffer your blood. Your blood typically gets no more than 7.2, and it goes down no less to 6.8. If it goes beyond that, it starts becoming problems. You start noticing issues, acid reflux, you know? So typically as you age, your pH is going to change a little bit because you're not taking in the water that you should be taking in, most likely, or you put on the extra weight, so you're not still taking in enough water to sustain the weight that you're at. So you have to sit there and drink water. So water acts as a nice little system. And in addition to that, you have a lot of minerals in your bloodstream to help you sit there and keep that pH around the same, okay? So this system is gonna work just like our normal acid-base situation. There's not gonna be anything different. It's gonna work exactly the same way. The only thing that's gonna be different is that you're adding a buffering agent. So you're gonna be adding something to the system to kind of shift the system, okay? So for example, so here is an example of carbonic acid and sodium hydroxide. So carbonic acid is going to be acting as a buffer to the sodium hydroxide, which is that strong base. And so as a result of that, this is going to be your product, right? And so that, again, it allows you to sit there and shift that pH and give you this really wide range where you can sit there and you keep adding and adding and adding and adding, and it's not going to alter the pH too much. Okay. So here, calculate the pH for a buffer solution with 0.5 molar lactic acid and 0.115 molar sodium lactate with a pKa of 1.38 times 10 to the minus 4. Okay, so what are we going to do?
You need your equation.
We always start with our equation. Okay, so we have what? What are our reactants?
Your lactic acid and sodium lactate.
So our sodium lactate isn't going to be our reactant, actually. That's actually going to be one of our products.
Oh,
Got it. Remember, it's just an acid-base reaction, and here we're just using water in the system. So it's
water.
Lactic acid
And water.
And water. And we're going to get
How are you getting sodium out of that, though?
You're not going to, so the sodium is just acting as a carrier for the lactate. All we're really getting out of it is the lactate. You're adding this to the system after the system already had reached equilibrium. It's going to shift that equilibrium. That's what you're going to be looking at.
Oh, okay, I see it now. Okay.
Yeah. So at the end of the day, sodium is going to be negligible because it's just, it's bringing lactate to the party. No, that's it.
Okay.
Okay. So in this case, then you're going to end up with H3O plus AQ. And you have to remember, you're bringing into the the system, and you know that lactate, sodium or group 1 metals with any type of polyatomic ion is going to dissociate completely. Group 1 metals always dissociate. It likes to be free. And so really they're going to be, remember when you guys remember doing total ionic equation?
Which one was that?
It's where you split up the ions and then you find the spectators and all that stuff.
Oh, yeah.
So sodium is going to be a spectator. So we're just kind of eliminating it entirely because it's going to be a spectator. Because you're putting it in there, literally you're putting it in the solution and you're letting that solution come to equilibrium. But ultimately, all you're putting it in there is to perform to get lactate. Okay.
Okay.
Yeah, it's funny how we think about chemical equations. Like when you're first learning chemical equations, you're thinking, okay, I put this in, and you don't think about it that your product is going to be in there too, and your product is being made as you're putting the stuff in there, right? We never think of it like that as being happening simultaneously in that same system. Okay, so this is going to be our chemical equation, right? And so, like I said, lactate is going to be acting as like a buffering agent. We're just throwing a little extra in there, okay? So in that case, if we have this equation, and is it balanced?
2, 4. No.
Are you
Wait.
sure?
Wait. 6, 7, 8, 5, 6, 7, 8. Yeah. Yes.
Okay, so it's balanced. So we know that it's balanced, right? So then in this case, we're just going to start off with what's given to us. We know that the lactic acid is going to be the 0.5. So we're going to go with our ICE table, ICE. Okay, so we go with our ICE table. We know that we're going to start off, our initial is going to be 0.500 molar of this guy. And then over here, we're actually going to start off with 0.115 molar. Now the difference is that we don't start off with any H plus. Or the hydronium ion. So we have 0 hydronium ion that we're starting off with. Okay. I should draw it like this so you guys know that this is just an extension of the equation up top, right? Or maybe I should let me make sure that there's no misunderstanding.
Okay.
Being lazy. I'd be saying, hell yeah, you are. You don't
Finish
know
strong, Dr. Henry. Finish strong. Just kidding.
I know. That's true. No, you're not lying. You gotta.
All those emails we're getting right now, I'm like, ugh. I'm
Yeah.
weeping. Stop.
Okay, so what is going to be the change? So if we have no H plus, what's going to happen? What are we going to do?
Put some X's.
We need some X's, right? All my X's live in Texas, right? So then we put our X's. So we know that the acid is going to be giving up something to make that H plus, because we know that that H plus is lacking. Okay, or we believe that H plus is lacking, right? Okay, so then our equilibrium, at equilibrium, we're going to have 0.500 molar. This guy minus X. This guy is going to be X. Actually, I should do this. erase that M. And then this guy is going to be 0.115 plus X. Okay, so if we set our equilibrium equation, what are we going to have? Ka is going to equal what?
Are we doing the products over the reactants? Ka?
That is correct. That's not always what it is. Never changes. It's always going to be products over the reactant. Right, Taylor. Go girl. Keep it up. Okay, so we have products over reactant. So we'll have that concentration of H3 plus times C3 H5 O3. Oops. Minus. Let me see if I can move that so that we have a little space. Oops. Okay. I'm having troubles today. Okay, so, and you said over reactants, right?
Yes.
And so we have our one little reactant, right? H, C, 3, H, 5, O, 3.
And you
Okay.
disregard water.
Yep, because water is a liquid, right? Remember, we don't
Oh,
take
yeah, yeah, yeah.
liquids or solids into account. Don't forget that. That's gonna get you. Okay,
Just testing you.
you're just testing me. That's good. I need to be tested, especially at this last leg, man. Okay, so we have that Ka. Let's put in those numbers. So up top, we have X times 0.115 plus X over 0.500 minus X. Okay. And we know what our Ka value is because they give it to us, right? Like 3.8 times 10 to the minus 4. You know, I think I'm going to start putting those questions on the side, you know, make some adjustments when I give myself room to write. Okay, so then we want to just solve for our equation, right? So we go through and do all the multiplication. So we'll end up with 0.115 X. I remember when I was in algebra, and I loved doing these problems. And then when you got the answer, you're like, yes. Back in the old days where they didn't have computers and you couldn't, you know, program it into your calculator. Nostalgia. Okay, let me pull up my calculator. Six 0.90 times 10 to the minus 5 minus 1.38 times 10 to the minus 4 x. Okay, so we want to bring all of these guys over to the other side. So we'll end up with x squared plus. Yep. So we'll have 0.115138. If we add this guy with this guy, minus 6.90 times 10 to the minus 5. And then we plug that into our quadratic equation, and that's going to equal 0.
Where did you get the second number, Dr. Henry? The 0.115138?
X, yeah. So when we bring this over, right, and this is 1.38, so then it's the addition of the two.
Okay, I didn't see the X on the other end.
Yeah.
I was adding the and subtracting, so.
I should use the different color since I have my ice table in yellow, so I'll remember that for the future. So then we're going to solve for x. X is going to equal, we're going to plug that into our quadratic equation. Let me pull up my quadratic equation. Of course, I don't have it up. Where is it? Sorry, working on a little curriculum. What is it? It's calculator soup. Okay, so let's plug in our numbers. We have 1 for A. We have 0.115138 for B. And then we have minus 6.90 e to the negative 5. Oops, negative 5, not 4. Let me put a 9 there. Okay. We want to calculate. So what's going to be the correct answer?
Well, you said it can never be 0 or negative, so it has to be the positive.
Let's just make it a 5.96 times 10 to the negative 4 molar. Okay. So that's going to give us our concentration of our hydronium ion. So how can we calculate the pH?
It's the log function, isn't it?
Yep. So it's pH equals minus log concentration of 5.96 times 10 to the minus 4. Okay, so you get pH.
3.22.
Okay. Piece of cake?
Yeah.
Yeah, the biggest thing about equilibrium problems is that they take a little bit of time, right? And you have to remember, you know, you're working with quadratic formula. So or quadratic equation. That's the hardest part. I love setting up the ice tables. The ice tables help me understand things, right? Initially, this is what I'm starting off with. There's going to be a change. Anytime there's a change, somebody has to give up something. That means something is going to be gained, because that's the law of conservation. If you ended up with something on both sides, then something went wrong, right? That is the law of conservation.
So, Dr. Henry, just confirming and making sure that I'm understanding correctly. The reason why in the change section of your ice table that the lactic acid is -X is because it's losing that hydrogen ion?
That's right.
Okay.
Well, and it's nice, not only you're losing that hydrogen ion, you're making your products, right?
Well, yeah, it's
So your products have to come from your reactants. They can't just magically appear.
okay. That is where I think I struggle, is remembering like what's X and what's negative and what's
Yeah, it's always thinking about it, because you think about it, you have to always have, okay, so it's like if you have 8 kids, right? And you brought a loaf of bread. Now you cut up that bread, your kids are going to eat the bread, right? So then you're going to be giving them the bread. Do you still have a loaf of bread if you've given bread to your kids? Right? No, you don't. You have no more bread. So you have to take from somewhere, give to something else. So your reactants are what you're starting off with. They're that loaf of bread, right? When you cut it up and give it away to your kids, that's your products, right? So they're gaining, the kids are gaining the bread, you're losing the bread.
Okay, gotcha.
Okay, kind of like money too, right?
Yeah.
Okay, so I'm going to say that bottom problem is going to work the same way. The only thing different is that you're going to be calculating grams of sodium acetate towards the end of the problem, right? Okay, so let's see. Okay, so I told you about your blood. Your blood is pH 7.4, roughly. I said 2. That's what I've learned in school. So, and a lot of that is due to it maintaining being buffered, right? So I said you have your bicarbonate system, which is often found in your gut and stuff like that. And so bicarbonate is often absorbed, kind of neutralize the acid in your guts when you're doing digestions, going through the digestive tract. Then you have the phosphate system, which we use phosphates for ATP. So that inorganic phosphate actually acts as a buffer as well as it's floating through the system. And then you have tons and tons of protein, soluble proteins that also kind of buffer the system as well. So all of these guys kind of work together in a nice little system to kind of keep your blood at the same pH, roughly around the same pH. But if you get too far off of that or too far below that, which it takes a lot for you to do, you have to be under serious physical stress to sit there and make that happen, drinking poison, or an organ not working at all. So things like that would.
Well, like a respiratory.
Yeah. And so like if you, respiratory diseases and stuff like that, cancer, things like that would cause your pH to also change, right? And lastly, your kidney plays a huge part in that. Not only your kidney, your kidney plays a huge part in it, but you also have the pancreas. The pancreas secretes a lot of stuff. One of the things that your pancreas secretes is biocarbonate, okay? I'm sorry, not bicarbonate. Okay, so often, because the value of the pKa is often really, it could be really small or it could be really large. It could have this huge fluctuation. We will often end up using the pKa because it's a lot easier to sit there and visualize, and you can linearize the problems in some cases. And then pKa is just going to be like pH minus log of your Ka. Okay. And so if you think about your equation, right, the equation that we have, that we've done so far, we know that the equation for Ka is going to be products over reactants. So we're going to use our generic case. The generic form of our Ka equation, right? So if we take the log of both of these, of both sides, or we plug this guy in here, if I could drag. Minus log A minus over hydronium ion. A minus times the hydronium ion over concentration of our acid. Okay. You guys see that so far? Mind if I move this to the side? If I move it to the side, can you guys see it in this corner up here?
Yeah, it's still there.
Okay, good.
Yeah.
Okay, so then if we sit there and we play with our equation, it's minus log So if we take this guy out, that'll be minus, which makes that, oops. Yeah. Struggling here. Can you guys see that? It says minus log the hydronium concentration of the hydronium ion, which we know is just pH, right? So we could sit there and say pKa equals pH minus the log of A, the conjugate base, over the acid. Okay, so this is a Hassenbach's, the Henderson-Hassenbach equation. Okay, so then if you have the concentration of your acid and the concentration of your base, then you can sit there and calculate your new, and you have the Ka value, you can calculate the pH for that solution. Right? So remember earlier when we actually have to go through and do the equation where we took all of that, this basically solves that whole problem. Right? Are you with me?
Yeah.
Yeah.
Okay. So you saw how long it took us to do that. So here, all you have to do is plug in what your concentration is for your conjugate acid, which in that case, it was like 1.15 for our conjugate acid, the molarity of that, divided by the concentration of our, the concentration of our conjugate base, which was the lactate, and then the concentration of the acid, which was 5.5 molar in the last problem. And then we had our pKa, our Ka. We can solve for our pKa. So we get log minus log. Heating here a little bit. Minus pH equals our pKa. Our Ka was, for the last problem, it was like 1.38 times 10 to the minus, I think it's 4. Okay, so if we took the log of that, minus log of Ka equals pKa. So that's going to equal minus log of 1.38 times 10 to the minus 4. So we get 3.86 equals pKa, sorry, equals pH minus, and if we take the, sorry, this should be log of this. So 0.115 divided by 0.5. Then we go log. So you get plus 0.638. So then pH is going to equal 3.222.
Oh, you're subtracting it. Yep. For the 0.63, you took the negative log or the log of the 1.5 divided by the 0.5?
It's the negative. It's the negative log of it.
Negative log. Okay.
Okay. So instead of having to do the entire ice table here, you could have just done it that way. Make sense?
So we can avoid the ice table altogether? No, just kidding.
Not always. Just under cases where you have your pKa or your pKb. This works for your pKb as well too. You just use the Henderson-Hasselbalch equation for that. Okay.
This is chapter 15, right, Dr. Henry?
This is chapter 14. We're getting ready to get into chapter 15. Okay, so Henderson-Hasselbalch equation. Okay, so this is just basically showing you, so here's your pH. This here is just showing you how flexible, so with the addition, we keep adding sodium hydroxide, and we see that the system is very, very buffered, right, because of that. And so you get very little change. Look how much change you get over the addition of a very strong base. Okay, so that just kind of shows you the concept of that resistance. Okay, so this is the equation here, although the way that they do it, I put the minus here so I don't have to worry about the products or the reactant. It means the same thing. If I flip this, then that makes this guy a plus. So then I would have my, oh no, that's right. It's exactly the same. The conjugate base over the acid. They just brought it over to the other side of the equation. Okay. Questions, concerns, Cash? And then again, this is always making the assumption that you have the 5% rule, okay, is valid. And that's usually the case with weak acids and weak bases anyway. Okay, so we just did that problem, so we won't do this problem here. It works exactly the same way. So you ended up with the same answers that you had before, so. Okay, so titration is just, concept of titration is finding that equivalent point for your acids. And basically, you're going to end up with a pH where you get neutralization, okay? Okay, and so this is just kind of taking into consideration both your acid and your base to sit there and work out the problems. They also give you the Ka for the situation. And here you just need to sit there and take into account that you have both reactions and you're going to be using your, well, in this case, it's a strong base. So really you're going to be relying on your acid and how it's going to be shifting your acid, okay? I'm going to save that. Last thing that I want to talk to you about is acid-base indicators. So you guys technically had, I was trying to save this for that problem, you had a cabbage indicator. Cabbage indicators are supposed to change colors over different pHs. So the red cabbage, it actually has a chemical that is altered by the addition of H's, the H plus ion, and it causes a chromatic change, and the product results in a chromatic change, so you get different colors. In life, we basically have isolated tons and tons of indicators from plants that all have chromatic changes. So as your pH changes, the color changes. And here is a table of that, and so you can kind of get an idea and the range that these dyes react in. So for instance, crystal violet is going to react between 0 and 1. So it'll go from a yellow to a blue color. Crescent red is kind of odd. It'll react, or it'll act in the range of 1 to 2, and then 7 to 9. And this guy will go from yellow to orange, and then from orange to red. I'm sorry, not yellow, red to orange, and from orange to red. Thymol blue acts at both two ranges as well. You have the red to orange here, and so that's from about 1 to 3. And then up here from 8 to 9, you'll have from yellow to blue. Okay, so this kind of gives you an idea. The most commonly used one is this phenolphthaleamine. I know I butchered that. This guy is the most commonly used indicator, and because it's real cheap, it basically will be clear and it will turn a light pink color. Yeah, I think you guys used that last semester for, you guys remember, I don't know, did we do the, I don't know, we didn't do it. Never mind, we didn't do it for your class. It was the year before, different lab. So your indicator, technically, if you play with your cabbage indicator, it's supposed to do that. However, I got gypped on the cabbage indicator, and I'm pretty sure, like 90% sure, that it's beet extract instead of red cabbage extract, because it did not change. It did only a 2-color change. From a strong acid, it'll turn really, really, really red. And then with its very, very strong base, it'll turn like a bluish color. So it's 2 extremes. And that's typically what a beet will do. Okay, so that's all chapter 14. If you look at it, it's all going to be exactly the same thing. Now for chapter 15 deals with solubility, right? Let me do that. Now, and it's the equilibrium of basically solubility and precipitation. You pull it up. Oops. I'm going to clear my screen. Okay, so when we look at and we think about precipitation, precipitation is what again?
Precipitant is gas. Or precipitant is the the floaties.
That's right, our solids. Yeah, when we get stuff coming out of solution. Yes.
Sorry.
Okay, so, and when we talk about dissolution or we talk about dissolve, the things are going to either precipitate or they're going to be dissolved, right? When we're working with ionic compounds, we're working with things that are going to either precipitate or they're going to dissolve. Okay, so there's an equilibrium to that, right? You get to a point where you reach an equilibrium where you have a precipitation forming under circumstances, or you have a situation where you have things, dissolve. There's going to be a equilibrium constant that is going to be associated with that solubility. It's called Ksp. Okay. So in the past, we've been kind of working with things that's just, okay, either it's going to be totally dissolved and stuff like that. If you get a high enough concentration, things are going to precipitate, right? So if we put enough salt, if you keep adding more and more salt to a solution, right, then you're going to get your solution is going to become what we call supersaturated, especially if it's heated up. And then eventually you're going to get to the point where you're going to start getting salt crystals forming because you've exceeded that point of saturation, right? You exceeded your Ksp, okay? So your Ksp is represented by just, let's say in the case of a generic equation, it's just going to be the same equation that we've been using the whole time, right? So it's going to be the product over the reactants. The only thing now, your reactant is a solid. It's a solid. And we know in the case of a solid, do we take that in consideration?
Those in liquids.
We don't take them in consideration, right? So then our Ksp is just going to be the concentration of our ions. So it's going to be in this case, the lead ion and the bromine ion. That's just going to be our Ksp. And since there's 2 of these guys, we have to remember that it'll be the exponent. So it's going to be using the exact same concept. Okay. So have you seen equilibrium is exactly the same thing? We just call it special cases. Oh, this is special, right? Not too special if you just go with that concept. Products over reactants, and you remember, you never take in consideration liquids or solids, right? You have to take into consideration gases or aqueous. Are you good?
Yeah.
Okay. So Ksp is often called the molar solubility. Okay, so if you hear that term, molar solubility of blah, 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 that's just talking about your Ksp. So calculate the molar solubility, calculate your Ksp, okay? So do me a favor, let's write the equilibrium equation for this reaction here. Solve what would I use to solve the molar solubility of this equation?
What's the same thing? Ksp equals mg over OH2.
Okay. That's right.
So you wouldn't divide them?
No, because these are your,
yeah. I got it.
so remember, products over reactants. Right now you have no,
It's a solid.
Yeah.
Okay.
Yes. Okay.
Coffee.
I know. Let's see. Okay, so that's pretty much it, right? And then if we wanted to sit there and calculate it, then we would have our Ksp. You're going to get equal amounts of both of these. So then you could just say x, in this case, it would be x cubed equals whatever your Ksp is, right? Okay. So if we have to calculate our Xp, and they told us that we have this many ions of this guy, then this guy is the ratio of it is going to be a 1-to-2 ratio, right? So then I'd end up with twice the amount of this guy, right? So let's see, they want us to calculate our Ksp in this case. So if we have 1.31 times 10 to the minus 4 molar of this guy, what is going to be the molarity of this guy? So for every one.
So you just square it, right? You just double it?
Well, you need to double it. That's right, because you need to multiply it by 2, because it's going to be this value multiplied by 2, because you're going to go 1.31 times 10 to the minus 4. And that's because it's a solution altogether. So it's molarity. We know that it's a 1 mole to 2 moles of Mg 2 plus to OH minus. So then those moles are going to cancel each other out. It also actually, really what it does, it cancels out the moles here, because this guy is moles of magnesium ion over total solution. So then the moles cancel out of magnesium ion, and you're replacing it with the hydroxide ion. So then this guy is going to be 2.62 times 10 to the minus 4. And so we're going to plug that into here. Make sense? Then we would just plug and chug. So I get 4.50 times 10 to the minus 12. Okay.
Yep.
Simple. So really, equilibrium is exactly the same thing, right? Now you're just working with a specific case. This is just dealing with solubility. That's it. Okay. Okay, so So let me clarify. So solubility. So when we talk about the maximum solubility is is the molar solubility. Is just going to be the concentration. Let's see. It's going to be the maximum solubility in molarity units for the substance in the molar solubility. So it's going to be that value, that concentration that you get for that for it staying in solution, right? So if we think about equilibrium, that equilibrium gives us when the things are in solution. If that concentration is greater than that, then it becomes a solid. It's going to be pushing it the other way. Does that make sense? So in our equation, remember Le Chatelier's principle? Remember Le Chatelier's principle. So in this situation here, if we exceed that equilibrium concentration, right? You have something that is greater than the equilibrium concentration. So in the case of the 1.31 times 10 to the minus 4, right? If we had this value at equilibrium concentration, so let's say instead of having that, we had 6.00 times 10 to the minus 4. Which way is it going to push the reaction? Is it going to go towards the products or is it going to go towards the reactants? If you increase the amount that you have here. Equilibrium is that perfect point where you're right at that point where you have things still dissolved. This is the point at breaking. You guys understand? As soon as you get to this point, you're going to start making this product. Are you with me? I'm hearing crickets. So let's see if I can explain it a different way. Okay. Equilibrium is a point where you have the existence of both products, right? So initially, a lot of times we start off with it all together, start off with it as a solid. Equilibrium means that you got to the point where you made as much of the ionic components that you can make, all of the possibility of dissociation that you can make under a situation or under an equivalency point. So in other words, what I'm saying is you have a solid, you're still making these ions that are going back and forth. And so you have solids being made at the same time you're having ions being produced. You've gotten a point where the rates of those are exactly the same. That's what equilibrium is, right? It could favor one, or the equilibrium could favor one or the other, but the point is that the rate of making a solid is the same rate as you making the ion. That's going to be your equilibrium. Okay, now if I put a whole bunch more salt, what's going to happen? Or I put a whole bunch more solid in, what's going to happen?
You're going to get more ions.
We're going to start getting more ions, right? It's going to shift. You're going to try to shift the equation to the other direction. So by me increasing this, right, it's going to, at the end, it's going to end up increasing these guys because they're going to try to balance each other out to get back so that you're back at equilibrium. Okay, so if I increase this concentration, if I throw in a whole bunch more of this, what's going to happen?
It's going to shift.
It's going to shift it the other way. Okay, so that's Le Chatelier's principle. So the maximum solubility is that solubility. It's what you have at equilibrium. It's that concentration that you have at equilibrium. If it's the concentration that we have at equilibrium, if we push above that, we're going to be shifting it towards here, right? And then if we go below that, it's going to be totally soluble. You know, if the concentration is below that, it's going to be all soluble. Does that make sense?
Yeah.
Yeah.
And if you think about it visually, okay, so if I put a whole bunch of solid in there, okay, I'm going to end up getting some more ions. If I keep putting more and more solution and I dilute the solution a whole lot, then I'm going to have almost everything in solution at a point. Everything is going to be soluble under the right circumstances, right?
Yeah.
So that's all that is, okay? So when they say here, calculate the max or the molar solubility for lead, they just want you to calculate the concentration of PB, you know? So that concentration. So in that case, if we did that, we just write the chemical equation for lead to bromide, you know that earlier, PB, Br2, solid, equals PB, plus 2B R. So then, in this case, it's minus, we get Ksp equals
PB.
PB
BR2.
oops,
Sorry, exponent.
2. Yeah, I knew what you were saying. And then we know that PB, so if we say PB is equal to X, the concentration of PB is equal to X. So then,
So you have to double your BR.
that's right. So BR would be 2X. Okay, so then we plug that into here, we get Ksp equals X times 2X squared. And so we get X cubed, or X cubed equals 6.60 times 10 to the minus 6. So we get down up here, X equals 0.118 molar. And that's PB 2+. Okay. So if your concentration is greater than that, then you know you're going to have solid being formed. If your concentration is less than that, you know that you're going to have everything dissolved. Make sense?
Yeah.
Okay. Okay, so common ion effect, basically, remember we had talked about Le Chatelier's principle. So if you're adding an ion, you can kind of shift that situation at equilibrium one way or the other. That's all you're doing when we're talking about the common ion effect. Okay, so if we're adding, so determine the effect of adding silver nitrate to a solution of silver chloride. What's going to happen? Now you got to the point where you have equilibrium already. So you have both the solid and you have your ions in solution. So if I add extra silver, because that's silver nitrate, remember, nitrate is one of those guys, it brings things to the party. It's always going to end up being effective in this case.
So you're going to get more ions then?
So you're going to get more ions of what?
The
So if I'm adding silver nitrate, as soon as you hit solution, it's going to dissolve. What's going to happen? That's going to increase what? Let me erase this other part down here, because that's kind of hard to see right now. Okay, right here. So we're saying, okay, right now we have this guy in solution, right? We have the silver chloride. So here's our cup, right? We have the silver ions down here, in solution, and this cup is filled with water. And then we have the chloride ion. Use this guy.
That's all I have. So.
Okay, so now, and then at the bottom we have our solid silver chloride.
Thank you.
Okay, so that here, this here represents solid, this represents the ion. You guys see that?
Mm-hmm.
Now, if I add silver nitrate, as soon as I add silver nitrate, nitrate isn't going to react with anything. It's not going to cause anything to precipitate. Nitrate never precipitates. Always going to be ionic unless we boil everything out, right? So we're going to add silver nitrate to our solution. That's not the best color. Lighter blue. So we're going to add silver nitrate. So what's going to happen if I add more silver nitrate? This guy right now, it's set up so that we have 3 of these guys that are coming up at the same time, and then we have 3 of them in solution. As soon as I add the silver nitrate, it's going to add an additional silver. What is that going to cause?
More of the chlorides to attach to create.
That's right.
Liquid?
The chloride is going to attach to the silver. Exactly. So it's going to shift our equation which way?
Towards the left, towards your solid.
It's going to be just shifting it towards the solid. Exactly. So the addition of just silver is going to cause the reaction to move in this direction. Right? Le Chatelier's principle, what we just talked about. Okay. So what's going to happen in the case of sodium chloride? So if I decide I'm going to add NaCl, what's going to happen in that case? Then group 1 metals, when they're with anything, they're going to dissociate completely.
It's going to do the same thing, right? Chloride is going to find those silvers.
Exactly. It is going to do exactly the same thing. So in this case, we're going to get for the sodium chloride, it's going to push it towards the silver, right? Okay. So if I decide I'm going to add more silver chloride to the situation,
Would you just have more ions then?
yeah, you just get more ions formed. Okay, pretty simple.
Once I see it visually.
Okay. Okay, so how are we doing on time? Okay, so basically we had just talked about that shifting and everything like that. So initially, we're going to start off with non-equilibrium conditions. We start off with non-equilibrium conditions. We're always going to start off with, instead of having a K, it's going to be a Q, right? So that Q is going to help us determine what's going to be happening. Is it going to be going one direction or is it going to be going the other direction? So if our Q is greater than our Ksp, a precipitate will be formed. So it's going to be shifting towards the precipitate. So that basically means that if our Q is greater than our Ks, our products are more than our reactant. If our Q is less than Ks, then our reactant in that situation has more. We have more of our reactant than we have of our products, and it's going to be technically shifting the other way. But if we sit there, we think about it. Really, we're going to have our Ks, and then we're going to have Q. In most cases, Q is going to be one way or the other, right? Does that make sense?
Yeah.
Okay. So that lower Q, that Q is lower than the Ks, you're not going to be forming a precipitant. It's going to stay in solution. Okay. Let's see. We're going to go ahead and skip this. This problem would be exactly what we did earlier with the Ksp, but this is just in the context of blood. Okay. So let me see. Okay, so we know that pH can actually affect pH can actually affect the products in this situation, because we know that in the case of magnesium will actually form a precipitate with the hydroxide ion. Okay, so in this situation, what you're going to be doing is that you're going to be looking at the formation of a precipitate in this case, right? Are you with me on this? You understand where I'm coming from? So in other words, you're looking at, if I'm looking at the magnesium ion, I'm looking at the magnesium ion plus, in this case, OH minus, okay? So in this situation, they want us to calculate the pH required for calcium hydroxide solution to precipitate the ions from seawater to obtain a 1.00 times 10 to the minus 5 molar magnesium ion concentration with a Ka of 8.9 times 10 to the minus 12. So again, we're looking at this equation. We're going to, if you look at the ice table, right? So in this case, we don't take this guy in consideration. So this is what we want at equilibrium, right? So we'll have our ice, ICE. You guys mind if I move this up top and on the side.
Sure.
So I have a little room to write. No sleeping there on me.
Working on it.
I know, it's been a long, long, long week. Okay, so what we're trying to figure out is what? So this is what we're going to have at equilibrium. That's our goal. We want 1.00 times 10 to the minus 5. Okay. This here is going to be our Ks. And then we need to calculate how much OH that we need so that we end up with this amount. Okay. So what we don't know is this. This is what we're calculating. This is going to be our X. So how much of this do we need to sit there and have that much? Okay.
So it's a 2-to-1 ratio still.
It's still going to be a 2-to-1 ratio, but the thing is that we're defining the concentration of this guy as X. So then that's going to be an important part here in a second, right? If we're defining it as this component, that would be something different. So if you look at this, this is going to be a pretty simple equation, right? So you're going to get your Ksp is going to equal your concentration of your magnesium ion times concentration of your hydroxide ion squared. Okay, so if we sit there and define it as this, that's just 1.00 times 10 to the minus 5
times X squared.
Times X squared. Yep. And then that's going to equal that 8.9 times 10 to the minus 12. So we get X squared equals 8.9 times 10 to the minus 7. And we get X is going to equal, square root . Oops.
Use 7.9
Okay.
times 10
Good.
to the negative 13th.
That should be the square root of that. So it should be a smaller value.
Oh.
That's 7.9.
I squared it. Hold on.
Yeah, I do that sometimes too. So I get
0.9.
So I got 9.3.
Yeah.
I'm sorry, 9.4.
Times 10 to the negative 4th.
Yep.
Yeah. Yeah.
Okay. So that would be our P. Oh, I mean, this would be our concentration of OH, right? OH minus.
So then you have to take the log, right, for the pH?
Right. We'd have to take the log of this guy. So the log of,
Negative log.
negative log of the concentration of OH is going to equal our POH. And then, so 3.03.
3.
Okay. Then our pH is going to be equal to our pKw minus POH. We know our pKw is equal to 14. So it's 14 minus our POH. And we know our POH in this case is 3.03. So then it's 14 minus 3.03.
10.97.
pH is going to be 10.97. Oops. Okay. Piece of cake?
Getting there, yeah.
Yeah.
Okay.
It kind of seems easier than the ice one, but I don't want to say that.
But it is the ice one.
It is, it's just not as in-depth, Abby. That's the
Uh-huh.
problem. This was an easy ice.
Why didn't
it's-
I learn this one first, though?
All right.
Because they teach you the general one, so you'll appreciate this one. That's what it is. Okay, so you guys kind of get the idea, right, of how it works.
So you're just adding on your
Yep.
steps to find either your pH, your concentration, your
So do you guys
Solubility.
remember the activity series?
I have it up.
Yeah. So if you guys remember, there's ones that are they're soluble in an acid solution, or they'll be soluble in a basic solution, right? And sometimes they're not soluble in water. Okay. Does that make sense?
Yeah, looking at the sheet.
Yeah. Yeah. And so this here is basically playing with that sometimes you don't get things that are going to be soluble because they're not going to be soluble. Okay. And then these are just some examples. So many ions are they're going to be either acid or base soluble. So for example, lead 2, mercury 2, silver, they're all insoluble under acid conditions. While iron 3, chromium 3, zinc, calcium are insoluble under basic conditions. Right. And so that you're going to have those circumstances. And so sometimes you're going to be presented with equations that are going to be along those lines. So if that's the case, you have to take in consideration, oh, right, these guys are going to be insoluble or soluble with that. So you have to take that into play as well too. Okay.
Okay.
Okay, and so this is just an example where we utilize that component, so wastewater treatment. So wastewater is treated to remove contaminants by adjusting to pH. So we can actually pH out certain ions as a result of that. We can get rid of them because we know that the characteristics are going to be insoluble. That means they're going to form that precipitant, and that's it. They're done. Going to be able to get it out of the system. Okay, so calcium hydroxide reacts with the potassium ion to precipitate out solution as this. Okay, so this is just an example of that. Okay.
Is that like the electrolysis and all that kind of stuff that they use?
Yeah, well, electrolysis is basically using electricity to get those ions out as well too. If you charge ions, you kind of just shift them out by using electricity, an electrical current.
Okay.
Yeah, so we can get really good water at the end of the day by doing that. If you know the composition of your contaminants. It also costs you a lot because you have to do so much.
Yeah.
We haven't made it cost effective yet. Okay. So the last thing that I want to talk about is the Lewis acid and bases. So we talked about Arrhenius, we talked about Bronson-Lowry. The last one is the Lewis acid bases. This also plays a huge part in organic chemistry. So you'll be reintroduced to this or introduced to this in organic chemistry more so than anything else. Okay, so rather than just looking at the hydrogen ion or the hydroxide ion, like we did with Bronson-Lowry or proton acceptor or proton acceptor and proton donor, then like we did with Bronson-Lowry, sorry. So rather, let me take that back. Arrhenius looked at it with just the ions, the hydronium ion and the hydroxide ion. And then we broadened the definition with Bronson-Lowry, where we looked at a proton acceptor, proton donor. Now, the Lewis model looks at it differently. It kind of changes it. Rather than looking at the proton, we're looking at electrons, right? So if you're getting rid of proton, now you're able to accept electrons. So the acid is going to be an electron acceptor, and a base is going to be an electron donor. Okay, so it's the reverse of the Bronson-Lowry in that sense. Bronson was looking at the proton, and then Lewis is looking at the electron. Electron acceptors are going to be acids, and electron donors are going to be bases. Okay, so when you're looking at organic chemistry, we organic chemists typically use the Lewis model or the Lewis definition of an acid and a base. Okay, Lewis acids will accept bonding pairs of electrons from a Lewis base. So that means the Lewis base is going to be donating the electrons. Okay, so the result is you're going to basically be looking at covalent bonds being created in this context. Okay, so it gives it a very, very broad definition because now you're just looking at the acceptance of electrons and the donation of electrons. We're looking at pair. Okay, so here are examples. So identify the following reactants as a Lewis acid or a base. Okay, what's happening here? Who's going to be my acid? Who's going to be my base?
So is the
The water, the acid.
Okay, so the water is going to be the acid. Okay, and the base is going to be the sulfur dioxide. Okay, that's true in this case. So, and what about the one below it? There's going to be accepting electrons.
That's negative. That's positive. So the BH3 is accepting.
That's right. BH3 is going to be accepting. It's going to be accepting the electrons from the oxygen, the oxygen ion that's going to be coming over, right? Or the oxygen molecules that are going to be coming over. So that would be accepting. So this would be my acid, and this guy would be my base. Lewis. Okay, you guys get that?
Yeah. It's kind of easier to think about it that way too, though.
Yeah. It's weird because I have a harder time thinking of it that way than all the other ways, but I get it, but it takes me a moment to take a look at. The last thing that I have to talk to you about is complex ion formation, where I really don't have a lot of time to talk to you about. So we have these ions that are capable of forming And what happens in the case of these complex ions, you have full covalent compounds interacting with the ion itself. So you'll have water interacting with a lead ion or something like that. So the lead is able to sit there and act as a ligand. I mean, the lead is able to sit there and coordinate the holding of various ligands, such as water or a chloride or chlorine situation. So it'll actually have these things bound to it in addition to it, and also have a charge associated. Okay. So there's an equilibrium constant that deals with the formation of those as well too. That's going to be your Kf, and so that Kf represents the equilibrium constants of formation. Okay. And so basically, it's going to be your Kf value is going to be larger than the numbers indicated of a favorable shift to the product form. So you're just going to be looking again at that Kf value. Okay. So it's going to be no different than before. Equilibrium constant is going to be done exactly the same way. Okay. And here's an example problem for that. We can't go over it because we ran out of time. So that's pretty much it. So I guess we're only going to get it to equilibrium. Kind of sucks. I wanted to get other things. So I kind of deep six this lab tonight. So if you guys can kind of look over the rest of the slides, you won't be responsible for that on your final. So what I'll do, I'll either give you the answers to those questions, or I'll just have you guys skip those questions and we'll pull in the answer. And if you, or I should say, if you answer those questions correctly, we'll give you extra credit points. We'll do it like that. How about that? Okay, so look over all of the notes, and you guys should have access to all of the notes at this point. I think I emailed them to you, and then I also uploaded, we uploaded it during Canvas.
Dr.
Okay.
There was an assignment. I just submitted it was extra credit for the forum, the community forum.
Yeah.
There was no submission, so I just submitted it into the comments, the picture.
Okay, so yeah, I'll fix that. Thank you, and then I'll fix that. I don't know why it didn't do that.
Okay.
I think I shifted it. I thought I made a correction to it already, but
Yeah. And then are you having office hours tomorrow?
yes, I have to, but I'm only going to be able to have one because I have students in their last presentation for 2A. So we'll have to shift it. And I'll email you the times because I have to look at the time.
Okay, just for tonight. So that's what I was just wondering.
Yeah.
For the lab.
Actually, that's my point. We're not going to do the lab because the lab has to do with electrochemistry, and we're not going to get to that, unfortunately.
Okay.
And so it doesn't make sense to put you guys through it. I think it's a fun lab. It'll be a fun lab to do, but it doesn't make sense to put you guys through it if you don't have the full thing.
Okay.
Yeah. So do me a favor, look over all the notes. You're not going to be responsible for the exam. And then, like I said, on the final, anything that you get in those questions. So answer all the questions, make an attempt on all of the questions. Even if it's just a guess, any points that you get extra will count as extra towards your exam. Okay?
Okay.
Okay. So sorry that we couldn't get through everything. You know, did the best I can do under this. The rest of the material, organic chemistry, you're going to see again if you take OChem, so you'll have that totally covered. And some of the other cases, so electrochemistry, you may see again slightly later on into higher courses, and thermo, you'll definitely see again. So most cases, most of you guys will. Fun form. But we also did kind of go over thermochemistry instead of going over full thermodynamics. So maybe next year I'll pull that together. Okay.
Does that mean we're not doing all of the homework in Chem 101?
That does mean that you get out of doing all the homework. So you're going to be responsible for equilibrium. If you've done homework already, it'll start adding to extra credit. But the thermochemistry, the organic, you're going to get a buy on. So it won't count against you. I'll make that adjustment.
But we could still attempt it for extra credit.
Yeah, you can still attempt it for extra credit.
Take it.
Okay. So, study everything that we've done up to equilibrium. So kinetics, all of that. So.
All right.
So we're not doing organic chemistry, coordination chemistry, and then electrochemistry.
And nuclear chemistry. Yep. So 4 topics. We're short by 4. Yeah.
Blame it on the Rona.
Yeah. Well, and technically thermodynamics, so technically 5. Yeah.
So then those 4 sections are not going to be on the exam?
So those sections won't be on your exam at all. They won't be on your
Okay.
exam, but they'll be on your final. Now, again, they're not going to count against you. They're only going to count as extra credit towards you. Does that make sense?
Yes.
Okay. And some of the thermodynamics is some of the stuff that you actually did in thermochemistry. So that part you're going to have a little bit responsibility for. So I'll weigh that depending on the question. But if it deals with entropy, you're not going to be fully responsible for entropy. We talked about entropy. If it's a concept question dealing general with entropy, something that we talked about in terms of the intermolecular forces, then you're going to be responsible for that, but you're not going to be responsible for the calculation of entropy or Gibbs free energy or anything like that. Anything that you get above that, if you guys get that and understand it, if you've already done it, then perfect, right? Answer the question. It counts as extra credit towards your exam. Does that make sense, Abby?
Yeah, that makes more sense.
Yeah, so anything extra counts as extra credit.
Okay.
Okay?
Sounds good. Once you get to your other class, Dr. Henry. Thank you.
Okay. I will see you guys. I'll see you guys. So there's no lab tonight because we didn't get to where I wanted to get to. So again, I'm sorry. I know labs are kind of fun and we didn't get to do as many as I'd like.
You said you were going to ship out the rest of the stuff for the wine?
Yes.
You're
Well,
going to post the directions or whatever?
yeah, I'll post the directions and I'll do a little video of the next steps because I'll be doing it with a bigger batch of wine. So
Okay.
you'll have directions for anything like that. But you still are responsible for bringing in a sampler for me to taste, even if, of what you've done so far.
How do you want us to bring it? Like a sample, like in a cup?
Yeah, well, in a water bottle,
Okay. I'm like,
Yeah.
I won't get in trouble for transporting.
Just have it sealed and,
Yeah,
don't have an open container.
Yeah. Thank goodness I have connections. I know everybody, but still.
Yeah. Okay.
All right.
Well,
Thanks.
I'm gonna let you go. I'm really late.
Have a good one.
You
Bye,
too.
everybody.
Bye.
Bye.